Now let's have a go at simplifying some complex Boolean expressions. The first one is x and y, or x and not y, or not x and y. We can apply the distributive law to take out x, the common factor in the first two terms, to produce an expression in which the first two terms have been converted to x and y or not y, and the third term, not x and y, has been left unchanged. Well, y or not y is always true, or equal to 1 if you prefer, so we can replace that parenthesized subexpression with 1, giving x and 1, still leaving the other term, not x and y, unchanged. X and 1 becomes x. And in the next step, finally, applying the relationship that a or not a and b is equal to a or b, we can convert x or not x and y to x or y. The next expression is a bit bigger. It has 4 terms, and one of them involves a mixture of and or operators. We'll start by applying the distributive law to multiply out that complex term, turning y and x or z into y and x or y and z. The other 3 terms remain unchanged. If we look at the result, we see that terms 2 and 4 could be minimized, and terms 1 and 3 also look as though they are susceptible to some sort of manipulation. Let's reorder the terms using the commutativity law, and then reorder the components of the first term, again using commutativity. This puts us in a position to extract common factors in the first pair of terms, and in the second pair of terms, using the distributivity law. The parenthesized expressions involving y and z both reduce to true, or 1, as I've written here. And we can eliminate the 1's to produce the minimized expression, x or y or z. Here's a third expression to minimize. You might like to follow through the steps on your own, without any commentary from me. We've seen that algebraic manipulations can generate a large number of alternative expressions which look different but which have the same truth tables and are thus, at some deep level, really the same. If we were mathematicians, we might say that they're isomorphic. In fact, any Boolean expression has an infinite number of isomorphs. Well, that makes life a little complex. When we're trying to minimize a Boolean expression, there are many transformations that we can perform at any stage, and it takes a certain amount of experience to be able always to choose the best transformation. Wouldn't it be nice if there was some simple rule that we could follow that reduced all this complexity? Well, surprisingly perhaps, there is. We'll start by introducing the concept of a canonical form, a standard structure for all our Boolean expressions that will make the subsequent manipulations simpler. This canonical form is the simplest form possible without loss of generality. Note that simplest doesn't necessarily mean shortest. Our ultimate goal is to produce short representations of the Boolean expressions which can be implemented using the minimum amount of electronics, but we start by generating a standard form in which every term includes all the variables. We'll start by introducing the name minterm. terms in a Boolean expression are minterms if they involve all of the variables and only the and not operators. If we're describing a situation in which there are n Boolean variables, then there are 2 to the power of n possible minterms, each one corresponding to a different combination of the values of the variables. So if there were 3 variables, there'd be 2 to the power of 3, that is 8 minterms. Not A, not B, and not C. Not A, not B, and C. Not A, B, and not C, and so on. It's probably easier to recognize the order of the minterms if we relate them to the lines in a truth table, where the standard pattern of columns with alternating zeros and ones in the rightmost column, alternating pairs of zeros and ones in the next column, and so on, can be read as a sequence of binary numbers down from the top, 0, 1, 2, 3, and so on. Well, the minterms are the Boolean expressions corresponding to those entries in the truth table. To reiterate, each minterm contains all of the input variables and only uses the and not operators. So now let's invent some function q of the inputs a, b, and c. The behavior of that function is captured by the pattern of zeros and ones in the output column. And we can transcribe that pattern by writing down all the minterms that are adjacent to the ones in the output column. Informally, we can say that wherever there's a 1 in the output column, there's a corresponding combination of inputs, the adjacent minterm, for which the function must produce a true output. And if any of those minterms is true, the function must be true. So we can write down a Boolean expression for q simply by writing out all the minterms that generate a 1 in the output column. And since if any one of those minterms is true, that's enough to make q true, we put OR operators between the minterms. This representation arises naturally from the truth table and is called by various names. It's the OR of AND forms, because the AND operators have higher precedence than the OR operators. We evaluate the AND components of the expression first, and then OR the results of those terms together. So OR of ANDs describes the order of evaluation of that overall expression. It's also referred to as the sum of products form. This also illustrates the order of evaluation of the operators. And if you want to seem especially erudite, you can call it the disjunctive normal form. The reason that there are so many different names is a reflection of the fact that Boolean algebra has, in spite of what the Oxford and Cambridge academics used to say about it, it's turned out to be so useful in so many different areas, and the specialists in every area have invented their own terminology. I'm afraid that learning a lot of equivalent names and notations for the same thing is the price you pay for studying something that has broad applicability. In any case, whatever symbols are used to represent it, the canonical OR of ANDs form is a very standardized representation for Boolean functions. It's very easy to generate from a truth table, and if you do generate it from a truth table, you can be sure that it captures all of the function's behavior, because the truth table lists the function's behavior in every possible circumstance for every possible combination of inputs. So that's all good. Boolean expressions, expressed in OR of AND form, may be a little larger than some other equivalent Boolean expressions, but they act as a good starting point for minimization. So if we got the truth table right in the first place, we can be sure that the OR of AND's representation completely describes a Boolean function, and that if a minimization is possible, we're ideally set up to find it. There's a minimization technique that starts with disjunctive normal form and applies some comparatively simple graphical rules and guarantees to minimize the expression as much as possible. It takes a bit of learning, but once you've got over that initial hump, it's really easy to apply, at least for problems with up to 4 or 5 variables. You don't want to try minimizing Boolean expressions with more variables than that, by hand in any case. So, what's the mathematical basis of this graphical technique? It's a relationship that we've encountered already. If we find an expression of the form a and b, or a and not b, then we can reduce the expression down to a in 2 steps. First, we apply the distributive law to extract the variable a, leaving a sub-expression b or not b, which reduces to true, or 1, and that when ANDed with a leaves a. And once we start looking for that pattern, we see that it turns up quite often. We can look at something like the original expression and say that it says that a has to be true, but b could be true or false without affecting the result. So, informally, a must be true, but b doesn't matter. This pattern comes in 3 flavors. For example, the first term could be inverted. We could have a and not b, or not a and b, which would reduce down to not a. On examining the expression, we could say that it's saying that the first variable has to be false, but the second one doesn't matter. So, let's write down the patterns that we're interested in. First of all, if our expression has a term a and b, and another term a and not b, so that the first variable is identical to the second, so that the first variable is identical in both terms, and the second variable is inverted from one term to the other, and those 2 terms are ored together, then the result is identical to the first variable, a in this case. In fact, that's the first example that we had at the top of the screen. Next, if we had an expression involving a term not a and b, and another term not a and not b, then again, when we OR those 2 terms together, the second variable is eliminated, leaving not a. It doesn't matter whether the variable that's going to be eliminated is the first or second in the term, so an expression that ORs together b and not b and a will reduce to a. And an expression that ORs together b and not b and not a will reduce to not a. Furthermore, the order of the variables in the 2 terms doesn't have to be identical because commutativity allows us to arrange b and a to a and b. So, how do we put this minimization to work? Well, the process involves 3 steps. First of all, we draw up a truth table. Only this is no ordinary truth table. Look at the values in the input columns. Whereas if we treated them as binary numbers, they'd normally read 0, 1, 2, 3. Here they read 0, 1, 3, 2. Now, this is an essential feature of the technique, and the reason that it matters is that with this arrangement, each pair of adjacent input combinations is only 1 bit different from the next. 0, 0 and 0, 1 are only different in the right bit. 0, 1 and 1, 1 are only different in the left bit. 1, 1 and 1, 0 are only different in the right bit. And finally, the bottom input combination and the top input combination, 1, 0 and 0, 0, are only different in the left bit. Where to from here? Well, let's invent ourselves a Boolean function q. This can be described by the expression not a and b, or a and b. So now we add the output column to the truth table and insert appropriate values into that column, a 1 for each input combination that makes q true. That puts 1s in rows 2 and 3 of the table, which sets us up for the next step. We put a ring around any pair of adjacent 1s in the table. This corresponds to a pair of minterms from which one variable can be eliminated. If we look at the input column, we can see that in both of the corresponding inputs, B is true, but A could be true or false, and the minimized expression is therefore B. And because of the way that we've organized the input combinations, any pair of adjacent ones is associated with a pair of min terms that correspond in some way or another to the pattern. So wherever we see a pair of adjacent ones, we can eliminate a variable. So let's consider another Boolean expression. This time Q is equal to not A and not B, or not A and B. This time the ones are in the top two rows of the truth table. We ring them. Of course, it's hardly necessary in a simple case like this, but we'll see the benefit when we get on to more complex expressions. So we ring them, and then we look at the corresponding min terms. They show that Q is true when A is false, whether or not B is false or true. So the minimized expression for Q is not A. The third case has Q equals not A and not B, or A and not B. This corresponds to a pair of ones at the top and bottom of the truth table. Now, physically they're not adjacent, but if we wrapped the truth table around into a ring, then the two ends would finish up next to each other. The thing that matters with the order of the inputs in the truth table is the order itself, not where it starts. So if the first and last terms are somehow mathematically adjacent, even if they aren't actually adjacent, then we can put a ring around them. And by examining the min terms, we can see that the value of B is true, and A could be either true or false, so it really doesn't matter. So in this case, Q is equal to B. Finally, in this group of minimizations, if Q equals A and B, or A and not B, there are ones in rows 3 and 4 of the truth table. When we look at the input values on the left, we see that A is true in both rows, and B could be either true or false, without affecting whether or not the output of Q is true. So the minimized expression for Q is A. Now we've looked exhaustively at minimizing expressions with two terms, but the technique can also be used when the expressions have more than two terms. Here's a three-term expression: not A and B, or not A and not B, or A and B. We'll draw up the truth table, horizontally this time, because people often draw up the truth tables for K-maps horizontally instead of vertically. But note that the order of the input combinations again goes 0, 1, 3, 2, as in the vertical case, and we insert ones that correspond to the expression that we want to minimize. So the next operation is to locate a pair of adjacent ones and put a ring around them. Note that we don't put a ring around all three adjacent ones. That doesn't correspond to the pattern of min terms we're looking for. You can see that there are no sets of three adjacent input combinations that have identical values for one variable, and there's no way of arranging the input combinations to produce that pattern. So the ring goes around the first pair of adjacent ones, and we generate a term not A in the result. But there's still a 1 in the truth table that isn't represented in the result. At this point we get a bit tricky. We say that it's legal to reuse one of the ones in the earlier ring if it's convenient for us to do so. We'll finish off the minimization and then I'll explain why that's okay. We put a ring around the remaining one and whichever other one is adjacent to it. That, of course, is the middle one in this truth table. We can see that the invariant input in these two locations is B, and the value of A doesn't influence the result. It could either be true or false. So the final result has another term, B, added to it. Clearly, not A or B can't be minimized any further. Now, why was it legal to reuse that middle one in the second minimization phase? You'll remember that earlier in the course we established that A is equal to A or A. Of course you do. Well, here we're saying that the middle input combination, not A and B, can be replaced by not A and B or not A and B, which gives us two terms, one of which can be used in one phase of the minimization and the other of which can be used in the second phase of the minimization. Try doing the minimization yourself algebraically and you'll find that you have to duplicate the middle term, as I've explained, in order to get the minimized expression that we've produced using the K-map technique. Let's work on a more specific example. We'll produce a simplified Boolean expression for the state of the weather, when it is cloudy or fine or wet. Now, that in itself is trivial. We'd simply invent one Boolean variable for each condition and put them together with a couple of OR operators to produce a Boolean expression that reads much the same as the words on the screen. However, we are in this case constrained to describe each weather condition in terms of whether it's raining or whether it's sunny. So, when the weather's cloudy, it's neither raining nor sunny. When the weather's fine, it's not raining and it's sunny. And when the weather's wet, it's raining and not sunny. We're not allowing for sun showers here. We'll use the symbols R and S to denote raining and sunny, and we'll work through the minimization twice, once algebraically and once using the K-map technique. So, starting with the algebraic minimization, we transcribe the information we already know into a Boolean expression with three terms, each combining some value of R and some value of S. The first term in the expression has something in common with each of the other two terms. Not R is common to the first and second terms, and not S is common to the first and third terms. So let's duplicate the first term so that we've got something we can use in two subsequent reductions. Now we rearrange the order of the terms so that related terms are adjacent to each other. And we can reduce the first pair of terms to not R, because both terms require not R to be true, whereas S can be either true or false. Similarly, the second pair of terms reduces to not S. We've seen the reduction that occurs between the last two lines on several occasions. It involves three steps: applying the distributive law to produce a term with, for example, not S or S, reducing that to true, then eliminating the true because it's ANDed with something else, like not R. So this minimization has been slightly abbreviated. Now let's look at the K-map minimization. We draw up the usual table, being careful to write the input combinations in the correct order, and insert 1 in the locations that correspond to the conditions described in our original specification. Next, we put rings around pairs of adjacent ones. The first one's straightforward, but the second is another of those situations in which the so-called adjacent ones are actually at opposite ends of the truth table. Their adjacency is mathematical and not physical. Anyway, having done that, then we read off the minimized Boolean term for each ring. The first ring corresponds to a situation in which R must be false, but the value of S doesn't matter, so that is not R. And the second term, in which we're looking at the common part of the 0, 0 at the left end of the table and the 1, 0 at the right end of the table, corresponds to a situation in which the value of S must be false, but the value of R doesn't matter, so R can be ignored. So there's our minimized expression. We certainly had to know how to drive the K-map technique in order to produce it, but there was less creative thought required than in the algebraic minimization case, where we're always faced with the need to choose the appropriate algebraic operation to perform, sometimes deliberately increasing the length of the expression to make it possible to perform some future operation that will reduce it by a greater amount. there's quite a lot of skill required, especially as the problems get more complex. So as problems do get more complex, algebraic minimization gets more and more difficult. K-maps, on the other hand, remain tractable until you get to systems with more than about 5 variables, when they simply become too complex to draw. However, for complex systems, there are software minimization techniques that can handle any number of variables, and they're in fact generally based on the K-map technique. The last slide covered minimization of expressions with 3 terms. Now we're going to deal with minimization of expressions with 3 variables. They aren't the same thing. The variables are the a's, b's and c's and so on. The terms are the expressions that result from combining variables with the AND operator, a and b, or not a and b, and so on. So here we've got an expression that involves 3 variables, a, b and c. We can't write out a linear truth table that shows all the pairs of minterms that correspond to the pattern x and not y, or x and y. There are too many ways in which that pattern can occur if we restrict ourselves to writing out the input combinations in a straight line. So we fold the truth table up into a 2-dimensional structure. The combinations of the first 2 variables that we're concerned with, a and b, are listed as usual across the surface from left to right. Then the possible values of the third variable, c, are listed vertically down the left-hand side of the diagram. Now, each block of the map corresponds to a particular combination of values for a, b and c. The first term in the expression generates a 1 in the second column, second row, where the input combination is a false, b true and c true. The second term generates a 1 in the second row of the third column. And the third term generates a 1 in the first row of the second column. We won't bother to fill in the zeros because they just confuse the picture and make it more difficult to find the sets of ones that we're interested in. So now we start putting rings around pairs of 1s. The first one's simple enough. The vertical pair of 1s corresponds to input situations in which a is false and b is true, whatever the value of c. So it generates a minimized term of not a and b. The second one's only slightly more complicated in that we have to look at both the horizontal and vertical sets of inputs to find the invariant part of the input. The top row has b invariant, that is, b is true in both input combinations, whereas a could be either true or false. And in the column on the left, we see that c has to be true. Overall, this ring corresponds to any input combinations for which b is true and c is true. So we end up with a b and c term in the result. Now we come to one of the more attractive features of K-maps. They can be used to eliminate more than one variable at a time. Each ring we've drawn so far has resulted in a term in the minimized expression with one variable less than in the unminimized expression. Where a term originally had 2 variables, the minimized version has 1. Where a term originally had 3 variables, the minimized version had 2. But we can do better than that. A word of warning though, the conditions are stringent. The groups we're minimizing must contain a power of 2 1s. That is, they must contain 2 or 4 or 8, or if we were handling a really big Carnot map, some other power of 2 1s. And the 1s must be arranged into a rectangle within the truth table. A square is a special case of a rectangle, so it qualifies, but diagonal arrangements or L-shapes or more arcane shapes won't do. So let's look at a particular example. Here's a Boolean expression for a variable q, which we'll map out onto a truth table in the approved format. Note that we're still being careful to write the input combinations across the top in the order 0, 1, 3, 2, not 0, 1, 2, 3. When we move on to 4-variable K-maps, we'll write them in that order down the left-hand side too. We fill in the ones in the table in positions corresponding to the terms in the unminimized expression. Oh look, surprise, surprise, there's a power of 2 ones, that is, 4 of the little blighters, and they're arranged in a rectangle. Who'd have predicted that that would happen? We put our ring around the ones, well, it's hardly necessary in this simple case, and examine the K-map to find out which variables matter and which ones don't. In this case, the ring encloses a set of locations in which A could be true or false, so we eliminate A from the resulting term. B, on the other hand, is required to be true in all 4 locations in the ring, so the resulting term must have a B component. C, like A, could either be true or false, so it is eliminated. So we're left with a minimized term that comprises only the variable B. 4 terms in 3 variables, down to a single variable. Cool. You might like to derive this same minimized version of the original expression algebraically. It's a little more difficult than the K-map minimization. It's probably time to work through some K-map minimization exercises. Here's an expression with 4 terms in 3 variables. The K-map we draw up has exactly the same skeleton as the last one, which was also for a 3-variable unminimized expression. There are 5 terms, and we transcribe the information from those terms into the map. Now, remembering that the more ones there are in a ring, the more variables we can eliminate, we go hunting for the largest group of ones that conforms to the rules. That is, they have to be arranged in a rectangle, and there has to be a power of 2 members of the group. Well, that row of ones in the bottom line conforms. It's a rectangle. Pretty special rectangle, it's only 1 item high, but a rectangle nevertheless, and it contains 4 ones. So we can produce a term in the minimized expression based on the input combinations in that ring. When we look at those input combinations, we see that A and B can be any combination of values that they please. The only thing that has to be a particular value is C, and it has to be false. So the first term in the minimized expression is C. Well, where does that leave us? We have one lonely one that's been left out of the group. We could transcribe that directly into the result, but the corresponding term would involve all 3 variables, and we remember, don't we, that to eliminate as many variables as possible, we want to make the rings in K-maps as big as possible, and that they can overlap. So we draw a ring that includes the leftover 1 and as many other ones as we can get into a rectangular group that has a power of 2 members. As it turns out, there is only 1 other one. Still, it allows us to eliminate another variable, and the resulting term in the minimized expression has A and B both true, and C left out because it could be true or false. That was such fun. Let's try another. I really should get a life. Here's the unminimized expression. We draw up the corresponding K-map and insert the ones that encode the information in the expression. Now for the task of finding groups of ones that correspond to our 2 criteria. There's obviously a pair on the right and a pair on the left, but remember that K-maps loop around. So we can connect up those 2 groups into a single 4-member ring, which allows us to eliminate 2 variables. And the one thing that's constant in those 4 locations? Not B. So that's our minimized expression. And that brings us to the final feature of K-maps, don't care states. Actually, I'm going to introduce 4 variable maps on this slide too, but they're a comparatively trivial extension of what we've already seen. Don't care states. Let's imagine that we're busy designing a controller for the segments in a 7-segment display. That's a single-digit display of the sort found in calculators and digital watches. The display comprises 7 independently switchable segments. If they're all switched on, the display shows the digit 8. we can display the other digits by choosing certain subsets of the segments to switch on. Another way of looking at it is that each segment is turned on only for certain digits, and we can therefore write a Boolean expression to describe when each segment is on or off. For example, the segment at the bottom right is turned on when the display is displaying any of the digits 0, 1, 3, 4, 5, 6, 7, 8 and 9. Everything except 2, in fact. Now, it's an unfortunate fact that the binary number system, which is used in most electronic circuits that handle numbers, and the decimal number system that we use, don't match up very well. One unfortunate aspect is that to represent the decimal digits 0 to 9 in binary, we have to use a 4-bit binary number, which has a range of possible values of not 0 to 9, but 0 to 15. So there are 6 unused binary codes in a binary coded decimal digit. If we draw up a truth table to show whether the segment that we're interested in is turned on or not, we need 4 bits of inputs to get the necessary 10 combinations for the digits 0 to 9. Since this particular truth table is a Canard map, we need to make sure that the input combinations are listed in the correct order, both along the top and down the side. Check. They go 0, 1, 3, 2 in both dimensions. Now, to make sure that we don't make any mistakes, it's probably a good idea to label each location in the table with the decimal value that it encodes, because they don't all occur quite where you'd expect. Let's say that we're treating C and D as the least significant bits of the number. The first column of the table is easy. It corresponds to the values 0 to 3. Only, of course, because of the K-map's funny order of listing, the inputs in the table go 0, 1, 3, 2. The next column is also easy. It has B, the next most significant bit, turned on. Now that's the 4's bit, so it encodes the 4 digits starting at 4. That is 4, 5, 7 and 6. The next 4 input combinations would encode the numbers 8 to 11. Just for the moment we'll ignore the fact that we want to stop at 10. And if we look for input combinations that encode 8 to 11, we'll find them not in the next column, but in the rightmost column. And of course, they occur in the table in the order 8, 9, 11, 10. Finally, the third column corresponds to input combinations corresponding to the binary numbers 12, 13, 15 and 14. So the correspondence between the input combinations and the numbers is a little unexpected. Still, we've got it all labelled now, so it shouldn't cause us any further problems. Now, we're trying to specify when that bottom right segment should be turned on. It's on when the digit being displayed is 0, 1, 3, 4, 5, 6, 7, 8 or 9. It's definitely off when the digit being displayed is 2. But should that segment be turned on or off if an input combination corresponding to the numbers 10 to 15 occurs? Well, we don't really care. If that happens, something serious has gone wrong with the circuit that's driving the display, and it isn't the driver's responsibility to deal with it. If it really matters, something else should handle it, and if it doesn't really matter, well, then it doesn't really matter. So let's make those locations in the table show up as don't care states. If the circuit ever finds itself in that situation, we don't care what it does. So, first of all, let's just find out what would happen if we did the obvious thing and assumed that the segment should be turned off if any of those inputs in the range 10 to 15 occurred. Actually, before we start adding rings to the map, let's get rid of those numeric labels. They've served their purpose, and now they're just complicating the picture. There, that's better. Right, Now we're on the hunt for rectangular arrays of truths that contain a power of 2 members. How about the 2 pairs of truths, one on the left edge and one on the right edge of the table? That adds a term, not B and not C, to the expression. We can find one more 4-square group with the corresponding term, not A and D. Now, a long vertical rectangle with 4 truths. That generates a term, not A and B. And that's as far as we can get with this approach using simple minimization. 3 terms, each with 2 variables. An improvement, certainly, but we can do better. Now, let's reiterate. We don't care what the display does if the inputs 10 to 15 ever occur, because we know that they never are going to occur. So, if we decided that it was convenient for them to be true, then there's nothing to prevent us from doing so. So, now let's try the minimization again, assuming that the don't care states are actually true, if we think it's convenient to do so. Right off, we find a set of 8 truths or pseudo-truths in a rectangle. And that corresponds to a term containing only one variable, not C. There are 2 truths in the next row down, and they can group upwards to the right to form another rectangular group of 8, and the corresponding term in the minimized expression is D. That leaves only the true in the bottom row out of the minimized expression. How big a group can we put that into? Well, there you go, another group of 8, and the corresponding term is B. So, by simple minimization, without taking the don't cares into account, we get the first expression with 3 terms with 2 variables each. But by allowing the don't cares to be true, if it's convenient for us to do so, we've cut the whole thing down to 3 terms with only 1 variable in each term. By the way, although all the real truths in the K-map have to contribute to the eventual expression, we only include don't cares if it suits us. So the 1 in the bottom right-hand corner could be completely ignored. Seems a bit cruel to the poor thing, but, well, sometimes that's just the way you have to be. Now, this may all seem too good to be true, if you'll pardon the pun, so let's check that it's worked. Here's the complete list of possible 4-bit inputs. We've said that the output should be true if the value of C is 0, which corresponds to these input combinations. The next term in the minimized expression is D. And here are the input combinations where D is true. The final term is B, which corresponds to these input combinations. Put all these together, look at the decimal values that they correspond to, and we'll see that the values for which the minimized Boolean expression would turn on the display segment would be everything except 2 in the range from 0 to 9, which is exactly what we want. And if the segment would be turned on for 10, 12, 13, 14 and 15, who cares? We know that our circuit won't receive those inputs.